The ability to compute, to process information and solve problems has been a defining characteristic of human civilization. From the abacus to the smartphone, our tools for calculation have constantly evolved. The 20th century witnessed the birth of the electronic computer, a machine that has revolutionized nearly every aspect of our lives. These normal computers, as we call them, powered decades of technological advancement. But as our ambitions grew, so too did our need for even more powerful machines. This led to the development of supercomputers, capable of performing quadrillions of calculations per second. These behemoths of computation have become essential for scientific research, weather forecasting, and financial modeling. Now on the horizon, a new era of computing is emerging: quantum computing. This revolutionary technology harnesses the bizarre laws of quantum mechanics to solve problems that are impossible for even the most powerful supercomputers. Normal computers, from the device you're reading this on to the servers powering the internet, operate on a simple principle: bits. These bits are the building blocks of all digital information. A bit is a binary digit, existing as either a 0 or a 1. This binary system is the foundation of all computing. Just like a light switch being either on or off, a bit represents the most fundamental unit of information in a computer. This simple on-off state is what makes digital technology so powerful. These bits are grouped into bytes, usually sets of 8, to represent more complex data like letters, numbers, and symbols. This grouping allows computers to handle more intricate tasks. By stringing together these bits and bytes, computers can store and process information. This process is what enables everything from simple calculations to complex algorithms. They use complex circuits called transistors, microscopic gates that control the flow of electricity, to perform calculations based on these binary values. These transistors are the heart of modern computing. However, this binary system, while effective, has its limitations. It can struggle with tasks that require more nuanced or complex processing. Each calculation a computer performs is a step-by-step process. This methodical approach is both a strength and a weakness. For complex problems involving vast numbers of variables, this linear approach can take an impractical amount of time, even for the most powerful computers. This is where the need for more advanced computing methods becomes apparent. To tackle the most computationally intensive tasks, we turn to supercomputers. These technological titans are essentially clusters of thousands of interconnected processors, all working in parallel. Imagine a stadium filled with people each solving a small part of a larger problem simultaneously. That's the basic idea behind a supercomputer's power. This parallel processing allows supercomputers to crunch through enormous data sets and perform complex simulations at incredible speeds. They are instrumental in scientific fields like astrophysics, where they simulate the formation of galaxies, and in climate science, where they model the Earth's climate system with increasing accuracy. But even with their impressive capabilities, supercomputers are fundamentally limited by the same binary language of bits as their less powerful counterparts. Certain problems like simulating the interactions of molecules or breaking sophisticated encryption codes remain beyond their reach. This is where quantum computers enter the scene. Quantum computers represent a radical departure from traditional computing. They are not simply faster versions of our current computers. They operate on entirely different principles, harnessing the strange and counterintuitive world of quantum mechanics. In the quantum realm, the familiar rules of classical physics break down, and particles can exist in multiple states at once. This bizarre behavior, known as superposition, allows quantum computers to perform calculations in a fundamentally different way. Instead of bits, they utilize qubits. A qubit can represent not just 0 or 1, but a combination of both simultaneously. This opens up a world of possibilities, allowing quantum computers to explore vast computational spaces inaccessible to their classical counterparts. Qubits, superposition and entanglement, the secrets of quantum computation. Imagine a coin spinning in the air, not yet landed on heads or tails. This simple analogy helps us understand the concept of superposition in quantum mechanics. That coin is in a superposition representing both possibilities at once. In the quantum world, particles can exist in multiple states simultaneously. This is the fundamental concept behind a qubit. Unlike classical bits, which are either 0 or 1, qubits can be both at the same time. It can be both 0 and 1 simultaneously, allowing for a vast increase in computational power. This duality is what makes quantum computers so powerful, but the true magic of quantum computing lies in another phenomenon: entanglement. This is where things get even more fascinating. When two qubits become entangled, their fates are intertwined. This means the state of one qubit is directly related to the state of another. Measuring the state of one instantly reveals the state of the other, no matter how far apart they are. This instantaneous connection defies classical physics. This interconnectedness allows quantum computers to perform calculations across all possible values of the qubits simultaneously. It's like having multiple processors working together in perfect harmony. This parallel exploration of possibilities is what gives quantum computers their potential to outperform classical computers for specific tasks. They can solve complex problems much faster. It's like flipping a coin once and getting information about every possible outcome of 1,000 flips. This is the revolutionary power of quantum computation. Google's Sycamore, a quantum leap forward. In 2019, Google made headlines by claiming to have achieved quantum supremacy with their 53-qubit quantum processor, Sycamore. This meant that Sycamore had performed a specific task that would be practically impossible for even the most powerful classical supercomputer to complete within a reasonable time frame. The task involved verifying the output of a random number generator. While seemingly trivial, this problem becomes exponentially harder for classical computers as the number of qubits increases. Sycamore, leveraging the power of superposition and entanglement, completed the task in a matter of minutes, a calculation that would take a classical supercomputer thousands of years. Quantum supremacy, a controversial milestone. Google's achievement sparked debate within the scientific community. Some hailed it as a watershed moment, marking the dawn of a new era in computing. Others argued that the task chosen was specifically designed to favor quantum computers and did not demonstrate a practical advantage over classical methods. The debate highlights the nascent stage of quantum computing. The technology is still in its infancy, and many technical hurdles remain before it can be applied to real-world problems. Building stable and scalable quantum computers is incredibly challenging, and the qubits themselves are highly susceptible to environmental noise, leading to errors in computation. The challenges of quantum computing, a long road ahead. Despite the excitement surrounding quantum computing, several challenges remain before it becomes a mainstream technology. Building stable qubits is a major hurdle. These quantum bits are extremely sensitive to their environment, and any slight disturbance can cause them to lose their quantum properties, leading to errors in computation. This decoherence is one of the biggest obstacles to building large-scale, reliable quantum computers. Another challenge lies in developing quantum algorithms, the sets of instructions that dictate how quantum computers process information. These algorithms are fundamentally different from classical algorithms and require a new way of thinking about problem solving. Finding quantum algorithms that offer a significant speedup over classical algorithms for real-world problems is an active area of research. The quantum future, from drug discovery to unbreakable encryption. Even though quantum computing is still in its early stages, its potential applications are vast and transformative. This emerging technology promises to revolutionize various fields by solving problems that are currently beyond the reach of classical computers. In medicine, quantum computers could revolutionize drug discovery by simulating the complex interactions of molecules, leading to the development of new drugs and therapies. This could drastically reduce the time and cost involved in bringing new medications to market. In material science, they could help design new materials with unprecedented properties, such as superconductors that operate at room temperature. These advancements could lead to more efficient energy transmission and storage solutions. Quantum computers also pose a significant threat to current encryption methods. The immense processing power of quantum machines could potentially break the codes that protect our online data, making cybersecurity a critical concern for the future. These computers could potentially break the codes that protect our online data, making cybersecurity a critical concern. As a result, the need for new, more secure encryption methods has never been more urgent. However, quantum technology also offers a solution: quantum cryptography. This cutting-edge approach leverages the principles of quantum mechanics to create encryption methods that are theoretically unbreakable. This new form of encryption uses the principles of quantum mechanics to create unbreakable codes, ushering in a new era of secure communications. It promises to safeguard our data against even the most sophisticated cyber threats. The journey into the quantum realm has just begun, and the full impact of this revolutionary technology remains to be seen. As researchers continue to explore and develop quantum computing, we can only imagine the possibilities that lie ahead. But one thing is certain: quantum computing has the potential to reshape our world in profound and unpredictable ways. The future is quantum, and it is closer than we think.